All right, so here we are on 1.4 today. This is the last section of chapter 1. 1.4 talks about inverse of relation. So this is, I would say, quite different from the first three sections. The first three sections talk about transformations, right? So A, B, H, and K, and what that does to a function, how it stretches it, how it flips it, how it moves it. This one is a bit different. We're not focusing on transformations. We're focusing on what is called an inverse function, or an inverse of a relation. So, understanding inverses graphically and conceptually is kind of the first part of this lesson here. So, an inverse is something that reverses position, order, or an effect of an action. Okay, so when you think about the inverse of a function, we are reversing sort of the mathematical operations in the function a lot. And as a matter of fact, what you'll see later is there is a reversal of the x and y coordinates when we're graphing. So inverse is going to mean reverse. You have to remember that little phrase, okay? Inverse means reverse. So whenever you undo something that you or someone else did, you are using an inverse operation. Whether it's unwrapping a gift someone else wrapped, or closing a door that someone else opened, or deciphering a code that someone else created. So in mathematics, an inverse undoes what a relation or function does. For example, if a function adds 5 to a number, its inverse subtracts 5. And I put this, these are two examples of equations, of functions and their inverses, both the equations and the graphs. So I put this one up here because I did want you to kind of see, and we'll go over how to convert one to the other, but notice that in the function, we have x being subtracted by 5 and being divided by 2, right? And the inverse, the division by 2, turns into a multiplication, right? This division turns into a multiplication, and this subtract 5 is seen there as a plus 5. So we're undoing what the function does, in a sense. The graph, okay, if this is your, if this in blue, if this is your original graph f of x, then the inverse graph is this green one here. And we will see that that there is a relationship between these two graphs and the y equals x line. So graphically, you'll see that there's a bit of a mirroring going on here. Yes?
For that example, x minus 5,
yep.
Why don't you multiply 5 by 2?
Well, we'll dig into this a little bit later. Yeah, we'll dig into this a little bit later because there's a few steps that need to happen. It's not as simple. It's not as simple as, I mean, I know you're looking at this, the 5 divided by 2. Why don't we do the 2 times 5? This is contained here. So anyways, it's a little bit more complicated than that. I just wanted you to see that there are opposite operations involved, but we'll get into the nitty-gritty of the steps there later. Okay? All right, so let's talk about what a relation is versus a function. A relation is a set of ordered pairs x, y. A function is a special type of relation, and we talk a lot about functions in math and in these classes. So f of x is function notation, and that means that there is a definite description of the y variable, okay, or the f of x. There's a definite description that includes x, and for each x there's only one y partner value. And so a function, like this would be a relation. If we had something that looks like this, there would be a relation between x and y, but because for some x's, like this x value right here, it has more than one y value. So this graph right here, this y graph, this blue graph, is not a function. And we've talked about vertical line test before, right? If you can draw a vertical line through a function and it hits more than once, it's not a function then. It's just a relation. So a relation is any set of ordered pairs x and y. It does not have to be a function. But most of the time we're dealing with functions in math, okay, for sure? So to find the inverse of a relation, the x and y coordinates are reversed. So as I mentioned, inverse means reverse of the x and the y coordinates. Okay? This means that for every list of points on a function that would be listed as xy, which is the common way to list them, right? The x value first, then the y value, and you got a point there. So every point on function f of x becomes flipped. They become y comma x for the inverse. So inverse means reverse, and we are reversing x and y. So here's a little graphic. This is in your notes as well. If you have a function that has a list of pairs like this, 2, 9, 4, 5, 11, 6, well, the inverse function must have these points where each point, the x and the y value are reversed. So 2, 9 becomes the point 9, 2. That's the mirror, the partner point on the inverse. 4, 5 becomes 5, 4, and 11, 6 becomes 6, 11. It also means that the domain of the function becomes the range of the other function. Okay, so they flip as well. So we're just kind of building this up. We're gonna have lots of examples, and we will be working with the math stuff. I'm just trying to give you an idea of what this all means, okay? So when graphed, so if we were to graph an inverse of a relation, oh, actually I should pause for 1 second. I think it's here somewhere where we talk about the, yeah, it's down here. Okay, I'll talk about it a little bit later. So when graphed, the inverse of a relation is a reflection of the original graph across the line y equals x. So this line kind of acts like a mirror. Remember, on that line, the x and the y are equal to each other. And so if you were to flip the points on that line, so like 4, 4, if you were to reverse those, it still is 4, 4. So that's the line that doesn't change. And in a sense, it acts like a mirror. So that when you're graphing an inverse of a function, you would use that y equals x line as the mirror, and then you would kind of sketch points across that line, and that's how you would get it graphically. And I'll show you some examples here soon. So any point on the original graph and its inverse will be the same distance from the line y equals x, but they'll be on the opposite sides. All right? So I'll bring back this diagram that I showed you here earlier. The domain of a relation is all possible x values. The range is all possible y values. When the relation is inverted, or you take the inverse, the domain and range swap. Okay, I mentioned that before. Okay, so everyone looking up here on the board here, you see this graph, f of x and f to the negative 1 of x. So the graph is f of x here, this blue graph, and notice that the inverse of this f of x is labeled as f to the negative 1 of x. That's the notation. We'll talk a little bit more about that in a few minutes. But these two graphs are like mirror images of each other across the y equals x line. And that's because each point on f of x, so this point right here, would be the point 1, 0. You see that? On the inverse, the x and y are reversed, and so this point becomes this one, 0, 1. They just switch places. And so that is the mirror point, or the image point there of the inverse. And that happens all over the place. You have this one, let's do, 4, 2. Okay, let's do 4, 2, right? Well, that becomes 2, 4. That becomes this point. That becomes 2, 4. Just a note, whenever you're writing coordinates, x, y coordinates, a point, when you're representing a point, please make sure you remember the brackets, okay? You have to put the brackets. I'm not sure why this is, but I'm seeing a lot of people like listing a point and not using the brackets. It's not a point if you don't use the brackets, okay? You have to have the brackets around, parentheses there, the rounded brackets. It has to be around the coordinates to make it a point, okay? So try to make sure you remember that. All right, so if we did this many times over, we would see that all of these points, 2, 1 is 1, 2, and so on. They all have partners on the other side of the line. And if you put all those together and you keep plotting those, then you get the inverse point. So anything x, y becomes y, x, okay, on the inverse. All right, moving on. Any questions there so far? Inverse means reverse. The y equals x line is a reflection. Could we do some more? Yep, we could. If this is the y equals x line, okay, and if we had some kind of crazy function like this, well, we could show an inverse of that too, each point, okay, I'll do this in black, each point would have a mirror point on the other side of the line. This one would go over here. This one would go over here. This one would go over here. This one over here. This one over here, and so on. And so that you have a graph, when you connect all those points, kind of looks like this. An invariant point on the line y equals x, okay, for sure. Okay, kind of looks like that. You see how it's mirrored there. The blue graph is a function, okay? This one here, this black graph, this is not a function, is it? It's not a function because it does not pass the vertical line test. So not all relations are functions. A relation is a function that passes the vertical line test, so each x value corresponds to only one y value. I mentioned that before. The inverse of a relation is a function only if the original line passes what's called the horizontal line test. How many of you have heard of the horizontal line test before? You guys heard of that before? Okay, some of you have, some of you haven't. Okay. Well, the horizontal line test is very similar to the vertical line test. The vertical line test uses a vertical line to test if f of x is a function. So if a vertical line, so vertical line test, if a vertical line only passes through the function or through the graph, the relation once, then that relation is a function. Okay? The horizontal line test is when you would draw a horizontal line, and if the horizontal line passes through the relation more than once, that means its inverse will not be a function. So here it is down here, it's in your notes. If a horizontal line is drawn through f of x and passes through more than once, then that means that the inverse is not a function. Because of course this horizontal line would be this vertical line, you see? So if I invert all the points on the horizontal line, I get this vertical line, and this graph over here does not pass the vertical line test. So I'll zoom in a little bit on this graph. This red graph is y equals x squared. And this graph is the inverse of y equals x squared. This is actually x equals y squared. And you see how you just switched the variables. And if you solve for y, you get y equals plus or minus square root of x. X equals square root. Okay, that's a bit misleading there. So the inverse here, so then you have positive, this is the positive root x, is the upper part, and the negative root x is the lower part. Okay, so this is the inverse, and it has to be two parts because each part is a function. The whole thing is not a function. Okay. And we'll talk about that a little bit later. Sometimes when you have a graph that does not pass the horizontal line test, that means that its inverse will not be a function, but you can split up that inverse into two or more parts that would make it a function. Okay? So, and again, we'll talk about that a little bit later as we move through. Okay, any questions here so far? I know this maybe a lot so far. You've heard some of this before, vertical line test. Inverse means reverse. Are we okay so far? Okay. All right, here's an interesting graph. Sorry, was that a question? Question? Here's an interesting graph here. So this f of x, you'll notice, is just half of a parabola. This blue graph, right, is half of a parabola. Here's the other half. Okay, that's the other half. But it's not drawn. And the reason is this is because if you just section off half of a parabola, then its inverse, the inverse of that half, will be a function. Okay? So this green graph that you'll see here, and I'll try and get a green marker. So this green graph here that you see here is a function because it passes the vertical line test. Any vertical line only hits the graph once. And so if I take a section of a graph sometimes I can draw the inverse of that, and that inverse will also be a function. Okay? So you see how the y equals x line is a mirror line there. Okay? Some points remain unchanged when reflected across the y equals x line. These points are the points that lie directly on y equals x, and they are called invariant points. So this point right here, 0, 0, and this point, 1, 1. Those are two invariant points because they're the same points on both the function and its inverse. And remember that invariant means it does not change. Okay, is this coming across okay? Pretty plain so far? Are we good? Graphically, it's the inverse of a relation is the reflection about the y equals x line. And algebraically, we're going to get to that here soon. Okay? So inverse functions and algebraic methods. Okay, if a relation is a function and its inverse is also a function, just like we showed you here, okay, the inverse is called an inverse function. And there's special notation for that. So f to the negative 1 of x is the notation for an inverse function. So f of x, that's part of it, it's a function, and the negative 1 means the inverse. So this does not mean 1 over f of x, it means the inverse of f. So that's important. This is the reciprocal, okay? That's the reciprocal of f of x, okay? That's reciprocal of f of x, okay? This is the inverse, and that's where x and y are switched. Okay, because on your calculator you actually might see this to the negative 1 button, which that to the negative 1 button on your calculator, sometimes it means inverse and sometimes it means reciprocal, honestly. So it is kind of confusing. So let's see. On this calculator, this button right here, x to the negative 1, that is actually reciprocal. That means 1 over x. But the second function of sine and cos and tan, do you see how there's a negative 1 there? That means inverse. So you got to be kind of careful. Even on calculators, it can confuse you a little bit. So I'm actually just going to take a snip of that here. Let's see. Okay. Okay. So if I just put this up there somewhere, then what you'll see is that this is reciprocal. Okay, that's recip. And then these to the negative 1s above the sine, cos, and tan, that's inverse. Okay, so you got to be careful there. You got to be careful there. When we're talking about a function, that negative 1, and in this spot right here, it means it's an inverse, okay? All right, so we talked about graphically, let's talk about algebraically. So how do we get, Sam, you asked about that one equation, how do we get from the explanation of a function, so the algebraic expression of the function, to the algebraic expression of the inverse? Okay, how do we get to there? So to determine the inverse algebraically, so that's just with the equation, with the numbers alone, not the sketching of the graph, we're going to follow these steps. So the first thing we're going to do, if it's in function notation like f of x, we're going to replace the f of x with y. Then, point 2, we're going to interchange or reverse the x and y positions, and then solve for the new y. This will be the inverse of the function, okay? And again, for now, don't worry whether, is it a function or not? Just, we're going to write f to the negative 1 of x as the inverse function, okay? So we won't worry whether it's technically a function or not for now, all right? All right, so let's do this example here. We have some space. I'll leave the steps up here. Okay, what is the equation for this black line here? Let's do that one. So the black line, f of x, let's do that. What is the equation for this line? Sorry? Y equals, or f of x equals? Sorry? 2x plus 1. Okay, does anyone agree with that or disagree with that? 2x plus 1? Okay, can you tell us real briefly how you got that? That is correct.
The intercept is 1, and then for every time x is added 1, it goes up by 2.
Okay, very good. The intercept is 1, so that's b. And if you take the slope between these two lines, it's a rise of 2 units and a run of 1. So that's 2, a slope of 2. So you have 2x plus 1. Very good. And that is something that all of you should be able to do pretty quickly, okay? Get the equation of a line, especially when you see the x-intercept, and you can easily calculate slope between any 2 points. The slope-intercept form, y equals mx plus b, pretty important. You should also be able to get graphs of parabolas now with the vertex graphing form and with all of the translations and transformations that we've studied. You should be able to identify equations of lines and parabolas pretty easily. Okay, what we're going to do is we're going to try to find the equation of this. This is f to the negative 1 of x. This is the inverse, isn't it? And you see graphically it's the inverse because here's the y equals x line, and the blue graph is a reflection from that y equals x line. So anytime that the f of x passes through y equals x, that's an invariant point, which it is. This point 0, 1 has a mirror point 1, 0. This point 1, 3 has a mirror point 3, 1. And so graphically we can see that that is the inverse. Let's find out what to do now. How do we get that equation for that line algebraically? So I'm going to replace f of x with y first. That's the first step. I'll just back that off so you can see there. Okay. Now I'm going to switch or reverse x and y. Okay. So you have write your functions so that there's y and x in there, then reverse y and x. Now that we've done that, we're going to isolate or solve for y now, which this is going to be pretty easy. We're going to subtract 1 from both sides. So we have x minus 1 over here equals 2y. And then I'm going to divide by 2 both sides. And so then I'm going to get y all by itself over here. And this one over here, I'd probably separate this a little bit. So this is going to be 1/2 x minus 1/2, right? Or x divided by 2 minus 1 divided by 2. So when I do the final step, I'm going to rewrite this. I'll do it in I guess I'll keep it in blue. F to the negative 1 of x, that's the y now, is equal to 1/2 x minus 1/2. And what I want to do is I want to check to see if this actually is the equation for this line that I see graphed here. And the slope is 1/2, so between this point and this point, I have a rise of 1 and a run of 2, so that checks out. And does this blue graph appear to pass through y equals negative 1/2? It does. So this appears to be true as well. So here's now where you have your, here's your equation there now. Okay? All right. Okay, so let's just talk about some summary notes here so far. So linear functions with a non-zero slope. So if we have a straight line that is not horizontal, it has any kind of non-zero slope, it always has inverses that are functions. So any straight lines with a non-zero slope always has an inverse that's a function. The slope of the inverse, and this is actually pretty important, and this was very important for my calculus class last week, the AP calculus class that many of you will be in. This is very important to note. We talked about this again, that the slopes between a function and its inverse, if it's a straight line, the slopes are reciprocals of each other. They're the same sign, but they're reciprocals of each other. This will always happen. So if you have a slope of 2, the slope of the inverse function, the inverse line, will be 1/2. So the slope of the inverse is the reciprocal of the original slope. And finally, because all the x and y values switch or reverse, the x-intercept and the y-intercept also switch roles. So where you have an x-intercept in one graph, that becomes the y-intercept. This is negative 1/2, 0, right here. And that's an x-intercept. And so that becomes the y-intercept, 0, negative 1/2. This x-intercept here, 1, 0, becomes the y-intercept, 0, 1. So they switch roles as well. Okay? How we doing? I know this is super interesting stuff on a Monday morning. I get it. I know. It's like your blood is flowing and you're just excited to actually practice this stuff on your own. I get it. Okay. Okay, let's go back. I want to go back to the very first example because there was a mention about this one. So let's take a look at this. I'm going to copy this. And let's just see if this is true, okay? We had a question about the 5 and the 2 and everything. So let's just check it out. I'm curious, and you guys might be too. So it has nothing to do with this diagram. Okay, but this is just kind of a bonus. So let me zoom in here. And let's see if this function actually does turn into this inverse function, okay? And so what I would do with this one, I'll replace the y with f of x. So I'll leave it like this, over 2. And then I'll switch. So now I have x equals y minus 5 over 2. Give him a punch. Give him a nudge. Reese? So what I want to do now is I want to solve for y. So watch carefully. I'm going to multiply by 2, both sides. Now I'm going to end up with 2x equals y minus 5. And finally, I'm going to add 5. So I have 2x plus 5 equals y. And I'll replace this y with the f to the negative 1 of x. 2x plus 5. Okay? And so it does check out. It checks out. So this 2 here, even though inside there was a 5 divided by 2, we are technically y over 2, 5 over 2. By multiplying once, that 5 over 2 becomes 5. So yes, this is x over 2, so that becomes a 2x. This is 5 over 2, that becomes a 2 times 5 over 2, or just 5. So it does work out. Okay? Good? All right. Okay, let's keep going here. Many functions such as quadratic functions do not have inverse functions because they fail the horizontal line test. So if you do have a function like a parabola that fails the horizontal line test, crosses more than once, that's called a many-to-one function, and the inverse will then not be a function. So it looks something like this, and it won't pass the vertical line test. Okay. However, an inverse function can sometimes be created by restricting the domain so that the function is just one-to-one. And that's what I had mentioned before. And this graph is a graph like that. If we restrict the domain of the parabola just to half of it, so there's like kind of like one arm of the parabola here, then the inverse will in fact be a function because I'm just taking half of it. So you will see that happen a lot in kind of real life situations. It'll happen, right? Like if this was time on this axis and this was like profit or something. So, there's no negative time, so there would be no profit associated with that. So we would often restrict the domain for real life questions. A one-to-one function, so that is a function where it passes the horizontal line test. So any horizontal line through a linear function passes just once. Any horizontal line through even a cubic function like this, that passes just once. So we would have an inverse that also is a function. Let's see. If I were to take the original away, I would have, where is it? I erased the wrong one. So I would have a function looks like this, right? So that's okay, that's good, that's still a function. So one-to-one functions pass the horizontal line test. Many-to-one functions do not pass the horizontal line test. All right, so that's the notes. That's the instruction part of the lesson. So graphically and algebraically, we can find inverse relations. The big thing is when x and y are reversed. Okay, inverse. Inverse means reverse. Graphically, it's a reflection about that y equals x line, and algebraically, you switch the variables and then solve for y. Any questions? Okay, good. Good. I see your notes package full of notes and diagrams. I see other notes packages that haven't been touched. Okay. Oh, well. Okay. All right. So if you have questions come up, please look back to your notes. All right. I'm still finding you guys are putting your notes away when you do your homework, and a lot of the answers that you have, a lot of the answers to your questions that you might have will be on your notes here now. Okay. Any questions? Yes, no, maybe so. Okay. All right, I'm going to set you off on your assignment here. Please work on that right now. And again, here are the notes for the inverse functions, inverse relations, graphically and algebraically.
She on Avatar.